Hello. In this lecture, we introduce even more examples of maps. I'll begin with a geometric example. Recall that we constructed a chain complex representing the linearization of a two-sphere by gluing together chains on the northern hemisphere and chains on the southern hemisphere along the equator. Although both the northern and southern hemispheres have a non-zero boundary, their difference has no boundary. In other words, it's a cycle of degree 2, i.e., it is co-represented by a map out of R bracket 2. Although the two halves of the equator are connected by hemispheres, they're connected in two distinct ways. The difference between these two ways of connecting each half of the equator forms something meaningful, a cycle 1 degree higher than the dimension of the equator. This cycle is conventionally referred to as the fundamental class of the two-sphere. Although this doesn't totally make sense at this point, I recommend thinking of R bracket K as a k-dimensional sphere. I'll now describe one way you can produce ordinary numbers from this theory. The necessary input will be a cycle V and a cocycle phi. We will produce a numerical invariant from this data by pairing the cocycle with the cycle. I'll do so by composing the cycle with the cocycle, obtaining a map from R bracket K to itself. In other words, their composition produces an endomorphism of R bracket K. Note that if I have a number, I have an endomorphism of R bracket K via multiplication. In fact, all endomorphisms of R bracket K are given by multiplication by some number. In other words, there's an equivalence between endomorphisms of R bracket K and numbers. In particular, a cocycle evaluated on a cycle is just a number. In many instances, this number admits a clear geometric interpretation. For the sake of laziness, let me just outline this example from complex analysis. Don't worry if you can't follow this, just concentrate on the conclusion. The cycle will consist of 1 over z dz, and the cocycle will be 1 over 2 pi I times the integral along a loop gamma. I'm thinking of both of these objects as living on the complex plane with the origin removed. This is reflected in the fact that 1 over z dz has an essential singularity at 0, and I want gamma to avoid this singularity. A classic result in complex analysis states that this pairing counts the number of times gamma winds around the origin. Note that this number is a, quote, qualitative invariant of the path, in the sense that it doesn't change if I perturb the path. Before moving to our next class of examples, let me introduce yet another important cochain complex, D bracket K. This complex is just R in dimensions K and K minus 1, and 0 everywhere else. The boundary operator is just the identity. As before, let's try to unravel the data of a map out of D bracket K into a general chain complex V. It's not hard to see that such a map coincides with the data of a vector W of degree K and a vector V of degree K minus 1. These two pieces of data must fit together continuously. In this instance, this means that you can compute V by applying the boundary of W. Note that in particular, there's really only one piece of data, as V determines W. Diagrammatically, the continuity condition also means that the following square must, quote, commute. Just to be clear, the filled-in part of the square indicates that going right and down coincides with going down and right. More formally, the composition of the top and right map equals the composition of the left and bottom map. Pictures like these are a common way to visually unravel these objects. Here are two basic examples. First, note that D bracket K plus 1 has a cycle of degree K. This is conventionally imagined as modeling the inclusion of a circle into a disk. In particular, the D is for disk. Second, note that D bracket K plus 1 has a cocycle of degree K. This can be visualized as making a sphere out of a disk by collapsing the boundary of the disk into a point. Let's say that we're given a cycle of degree K. We can endeavor to, quote, extend this cycle to D bracket K plus 1. More formally, we want to factor the cycle through the map from R bracket K to D bracket K plus 1. This type of factoring is commonly referred to as a, quote, extension problem. I'll leave it as an exercise to show that this factoring is exactly the data of a vector of degree k+1 whose boundary is the original cycle. When we can solve this extension problem, we call the cycle a boundary. Note that although the cycle is determined by W, the converse is not true. We can obtain a cycle from every boundary by restricting its associated map to its cycle. You should picture this composition as taking the boundary of the disk inside of V. You can also make sense of this algebraically, using the fact that the boundary operator squares to 0. Fortunately, not every cycle is a boundary, e.g., the fundamental class of the two-sphere. Another example of a cycle is a circle in the complex plane. This cycle is a boundary when considered as a loop inside all of the complex numbers. However, it's not a boundary if I remove the origin, introducing a quote hole. A word of caution. The common intuition of cycles that aren't boundaries as holes can be problematic for a number of reasons. For one, its meaning is totally vague and unclear. In some sense, it's based on a clumsy understanding of Alexander duality. But for now, it's a useful heuristic. Note that all maps from D bracket k+1 into R bracket k are 0. Try picturing what this is saying in terms of the pictures we've drawn of D bracket k+1 and R bracket k. Let's imagine we're given a cocycle and a cycle of V of the same degree. If we further assume that V is a boundary, this means that the composition of V and phi factors through a map from D bracket k+1 to R bracket k. In particular, phi of V factors through the 0 map and is therefore 0. In other words, cocycles evaluate to 0 on all boundaries. This derivation might feel a little queasy. I recommend showing this vanishing in a more algebraic point set fashion. The contrapositive of this statement is super useful, namely that a cycle is not a boundary if you can find a cocycle that has a non-zero pairing with that cycle. I'll say that again. A cycle is not a boundary if you can find a cocycle that has a non-zero pairing with that cycle. I invite y'all to think through what this is saying in the complex analysis example I presented in the previous slides. Next, let's imagine maps into D bracket k. As with maps into R bracket k, these have a more algebraic feel. I'll leave it as an exercise to convince yourself that a map into D bracket k is the data of a linear map phi sub k tilde from vk to R and a map phi k minus 1 tilde from vk minus 1 into R. These two pieces of data must fit together continuously. In this instance, this means that you can compute the value of phi k tilde on V by applying the boundary of V and then applying phi k minus 1 tilde. In particular, there's really only one piece of data, as phi k tilde is determined by phi k minus 1 tilde and the boundary operator. Given a cocycle phi, we can endeavor to, quote, lift this cocycle to a coboundary phi tilde. More formally, we want to factor the cocycle through the map from R bracket k to D bracket k. This factoring is commonly referred to as a, quote, lifting problem. When we can solve this lifting problem, we call the cocycle a coboundary. Note that although the cocycle is determined by phi tilde, the converse is certainly not true. Note that all maps from R bracket k into D bracket k are 0. Try picturing this in terms of the pictures we've drawn of R bracket k and D bracket k. Let's imagine that we're given a cocycle and a cycle of V of the same degree. If we further assume that phi is a coboundary, this means that the composition of V and phi factors through a map from R bracket k to D bracket k. In particular, phi of V factors through the 0 map and is therefore 0. In other words, coboundaries evaluate to 0 on all cycles. This derivation might feel a little queasy. I recommend showing this vanishing in a more algebraic point set fashion. As an exercise, I suggest using a region which bounds a loop gamma in 3 dimensions to produce a coboundary of integrating along gamma. Hint, use some variant of Stokes' theorem. We can use an n by n plus k matrix A to construct a chain complex, the cofiber of A. For simplicity, we'll assume that the rank of A is n. For example, A could be iota n, a matrix in reduced row echelon form. Geometrically, this is the inclusion of an n-dimensional space into an n plus k dimensional space as the first n coordinates. In the coming lectures, I'll go deeply into the cofiber construction. For now, just note that the data of a map from D bracket K into the cofiber of A can be identified with inhomogeneous linear systems of equations Ax equals y. A final cryptic note. A consequence of Gaussian elimination is the construction of a map from the cofiber of A into the cofiber of iota n, which is a bijection on each component. This isn't entirely obvious. You'll have to give a fair bit of thought if you want to see how this works. And that's all I have for today. Have a nice day.